In this lesson, we will find the derivative of the exponential function e to the x. The derivative, of course, can be found from first principles. That is, that the derivative is the change in y values over the change in x as the change in x approaches 0. Our function is e to the x, so we need to put x plus h into that function. We will get e to the x plus h, and our f of x is of course just e to the x over our h. Now the x plus h index there of course means that we can multiply the two numbers e to the x and e to the h. We can take out an e to the x out as a common factor there, and in fact we can take it straight out of the limit because there's no h in e to the x. So now what we're left with is to find this limit over here. We can try to find the value of that limit by substituting h equals 0 into the expression. We will get e to the 0 is 1, and our denominator becomes 0. So we'll end up with 0 over 0, which is indeterminate. That is, we can't work it out because we can't divide by 0. So we can have a look at a graph of that function to see what is happening as the h approaches 0. From the graph of the function e to the h minus 1 over h, we can see that the limit as h approaches 0 from above is y equals 1. And if we approach 0 from below, y still equals 1. So the limit of that function is 1. We can also work this out numerically by using a spreadsheet. Here we have a column for various values of h that are approaching 0, and we work out in the right hand column what our e to the h minus 1 divided by h is equal to for those values. And you can see as we go down that list that we are approaching the value of 1. So our limit here, we conclude, is equal to 1. So we'll use the fact that that limit is equal to 1, and so our derivative then ends up being e to the x times 1, which is of course just e to the x. Now e is a very special number. We give it the name Euler's number, and it's approximately 2.7. It's a special function, our e to the x, because the derivative of that function is itself, that is e to the x. No other function has that property of its derivative being itself. And it really means that the slope at any point on the function is equal to the y value. Here we have a slope of 1 and the y value is 1. At any point x, the y value will be e to the x, and the slope of that tangent line there will be e to the x. Let's explore that for various values of x. We've plotted the graph in GeoGebra, and we can see at the point on the y-axis where the y-coordinate is 1, and the equation of the tangent line there is y equals x plus 1, so the gradient there is 1. We'll move that point along a little bit so that our x value now is 1. Our y value there, as you can see, is 2.72, and our equation of the tangent line also indicates that the gradient is 2.72. We can use another value of x. Let's say we'll make x equal 2 there, and our y value is 7.39, and once again the gradient of that tangent line is 7.39. And of course that will also happen when we're to the left of the y-axis. Here we have x equals -1, and so our y value is 0.37. And you can see that the gradient of the tangent line there once again is 0.37. This is the case for any of those values of x. That is, our y value will always be the gradient of that tangent. So we've seen that the derivative of e to the x is e to the x.